Okay, so I know in front of a room full of believers, but I want to spend a bit of time motivating what we're doing. So why do we do program verification? So for example, what is the cost of a bug? I guess most of you have heard of the video game Cyberpunk. So I haven't personally played it, but one thing I know is that when it was released, it was full of bugs. Now, one big question is, were those important? Were those bugs important? And they were probably very annoying to the players, but they were likely not that important. Now, if you take one buffer overflow in the OpenSSL implementation of TLS, so that's Heartbleed, is it important? Well, with this one buffer overflow, you can steal social insurance numbers, hack hospitals, hack tax agencies, and this is one bug. And there are many other bugs and vulnerabilities like this, right? So there is some software which is extremely critical and in which the presence of one bug can cost a lot. Now the question is, of course, how can we improve on this situation? How can we develop secure implementations? Are testing and auditing enough? And so, of course, I'm trying to sell program verification, and most people here are believers, but I want to zoom a bit on cryptographic code, which is a topic on which I've worked a lot. So one problem with cryptographic code is that it is extremely critical. For example, the Heartbleed bug is linked to a bug in a cryptographic implementation. And one issue is that cryptographic code has to be extremely fast and optimized, and this is annoying. Okay, let me try something. No. Just doesn't work anymore. Is the screen on?
Screen is on, yeah. Try HDMI again. Can give you a clicker that helps you. USB.
Yeah, that would be good, I think. Come on. Yeah, maybe let's do that. Okay, do you have ouais.
Tu les as poussés sur qui?
Non, je ne les ai pas poussés. I try with mine maybe? Thanks.
Just bumping it.
But
Yeah,
No.
leave it. Do you still want this one?
no, I think it will be okay. It's just, yeah. Actually, yeah, let's just.
So the screen
Yeah.
not responding at the moment.
My laptop did pick up that I had,
My laptop did as well, yeah.
yeah. Okay. I'm sorry.
Yeah, exactly. 1 hour later would have been fine, but. Mm.
There's a box. I'm not gonna touch the box though.
Yeah. use the HDMI as well, but it works on no computer. So.
So I'm gonna ask at the reception, at the registration, whether we can borrow the TV. I think that's a good option.
Or maybe we just go to the room next door.
Or we get a different.
Yeah.
I'm still motivated to verify Rust, but I still want to hear why you want us to verify Rust.
I think your colleague is also trying to fix something.
The guy who was sitting there?
Yeah, he went to the staircase.
A few minutes, but I'm gonna do something there.
It started flickering, and so it was the connection up here.
He probably went and grabbed a new cable. That's why he has to go downstairs and come back. So it might take a few minutes. Do you have a?
Yeah, I've got an HDMI
I
here.
can check for meanwhile.
Yeah, we try. With a different computer.
Yeah, so it's the cable. He went to grab one. He's gonna change it. It might take a few minutes. I'm really sorry for the delay. But once he fixes it, it'll be running and ready to go.
So we're sure it's that cable, right?
Yeah, there's not like if he tried with multiple computer and it wasn't going.
No, I mean it can't be another cable.
The other cables are not connected, are for other, like are for the
Okay, I see.
microphones or
Okay,
stuff like that, so that's working. It's really just that one for the screen.
Okay. yeah. It's, yeah. Yeah, I plugged it in.
We can reflect that.
Yeah. Let me check. Yeah.
That looks good.
Good.
And we're back.
So, yeah, I can convince you to verify Rust programs now. Okay, so what's wrong with cryptographic code? Well, first of all, it is extremely critical, as we've seen, and also it's full of bugs. Why is it full of bugs? Well, because there are a lot of constraints here. The implementations must be extremely fast. And also there are security constraints, such as the fact that the code must be constant time. So the execution time on the code must not depend on secret data, because this is a side channel which can give information about, for example, your private keys, which can lead to those private keys leaking. So the consequence is that cryptographic code is extremely low level and optimized, and there are many bugs lurking in there, and they are extremely technical. So for example, here is a bug report from the NACL library where they just swapped two variables in, a lot of lines of code, and these, of course, would not be coded by random tests. They managed to catch it by auditing, but this one, in the reference implementation of SHA-3, was not coded by auditing. And it's a bug in the logic of a very tricky state machine. And how to trigger that bug is also very technical. You need to call different functions with buffers of very precise lengths. And it was a pretty serious bug, which was because it's a reference implementation of SHA-3 got inherited by many libraries out there, including the standard library of Python. Now, those bugs may seem hard to trigger, but the problem is, in the context of cryptography, we're talking about security, so there are attackers actively looking for those bugs and trying to exploit them. So if there is one single bug, once again, think about the buffer overflow of in the TLS implementation, it can be exploited. Now, the good thing is we've got Rust, which saves us from many bugs, so it saves us from Heartbleed, but it doesn't save us from panic freedom and functional correctness bugs, like those two I've mentioned before. So this is why we do formal verification. I want to emphasize one thing in formal verification in the methodology, which is that we always verify with regards to a specification. So if the specification is wrong, the verification effort doesn't mean anything. So the specification is the source of truth. It has to be simple to understand, carefully tested, and audited. In the context of this talk, I'm going to focus on functional correctness. Now, with regards to functional correctness, there has been many successful efforts to verify cryptographic programs. And I was personally involved in Project Everest, whose goal was to develop secure components for the HTTPS ecosystem. The methodology was to write and verify code in the F-star proof-oriented language, and once the code was verified, we would extract it to a mix of verified C and assembly code, which we could then deploy in various real-world projects. It was a pretty successful project. It led to more than 300,000 lines of verified code, which was deployed, for example, in Firefox, Linux, WireGuard, or Python. And in the specific case of Python, we actually replaced the problematic hash implementations I've mentioned before, which means that today we are extremely confident that the kind of vulnerabilities I showed on the previous slide doesn't exist anymore on those specific implementations in the Python standard library. Now, this approach was very successful, but still, there are many questions, like can we go beyond that? Can we target largest class of programs by using the same methodology? And can we also speed up verification because it's a quite labor-intensive activity? And there are quite a few challenges. So for example, one big problem was that people don't like consuming automatically generated code. They don't just accept the code because it has been verified, because we tell them this code has been verified, it's free of bugs in some sense. They want to read the code, audit the code, check that it is idiomatic code, that it complies with their coding practices. And this leads to a lot of friction during PRs. So the way it would work is we would write and verify the code in F*, we would extract it to C, then someone would review the code and say, oh, I don't like the shape of that, could you modify it please? And then we would go back to the F* code, identify the part of the code which is responsible for this snippet, which is not completely trivial, because there are many steps happening in the transpilation. For example, many functions get inlined. So we identify the part of the code which is problematic, we tweak it, we fix the proof, regenerate the C code. Just replaying the proofs of the Hackelstar cryptography library takes around 40 minutes on a quite good machine. So there are a lot of frictions there. And another problem is, of course, that scaling is hard. Verifying some code takes a lot of efforts, and in particular because reasoning about memory analyzing is extremely tedious. So it's extremely hard for a software engineer to reason about aliasing. It's even harder in the context of formally verifying the code. So we want to simplify that. And finally, the F* proof-oriented language mostly relies on discharging proof obligations to SMT solvers. It works extremely well in many situations, but for the kind of projects on which I worked, we reached the limitation of that. So in particular, there's always a moment where we need an escape hatch, we need custom automation, for example. So this led us to the Aeneas toolchain. So following our experience on working on Project Everest, we decided to create a new verification toolchain with the following requirements. So first of all, we decided to target trust because it gives us memory safety out of the box, right? And also it allows to drastically simplify reasoning about memory, and I'm going to show you that just afterwards. We also wanted to have a very clean separation between the code on one side and the proofs on the other side. We wanted to have custom and extensible automation and also a more interactive toolchain because using an SMT solver is not always very interactive. So it led to the following framework. On the left, you write Rust code, and then you compile the Rust code to a model that we extract to an interactive theorem prover, here Lean. So basically a tool like F* to do proofs. So at its core, Aeneas is mostly a compiler, okay? It gives you a model of your Rust program. And very importantly, because Rust is very constrained, we can generate a pure functional model. That is, despite the fact that on the left, your Rust code uses mutable borrows, for example, or in-place updates, on the right, we do not have pointers at all. We have a pure model. We completely abstract away reasoning about memory, and in doing so, we can focus on the functional correctness of the code. Given this model, we can say and prove theorems about it, so functional correctness theorems, for example. And once again, I insist on that. What this design gives you is we have a very clean separation between the code written and maintained by the software engineers and the proofs written and maintained by the proof engineers. Of course, everything is replayed in CI. And by targeting Lean, we benefit from a highly interactive and extensible tool, which is very useful when designing custom automation that we really needed before. And also we benefit from many libraries like mathlib, so this huge mathematical library, which is very useful when reasoning about cryptographic code because it's a lot of maths. So this is the overview of the toolchain. Now let's dive a bit more into the technical details. So first of all, the big question is, what does this pure functional model look like? Because once again, on the left, I've got Rust code with, for example, mutable borrows and in-place updates. I'm going to show you this on this very simple example. So it's simple but slightly tricky because this choose function returns a mutable borrow, and the borrow it returns is not necessarily known statically. It depends on the value of the Boolean here, right? And I'm using it here. So the code on the left is, of course, handwritten, and the code on the right is the automatically generated lean model. So the intuition behind the model we generate is that we want, for this snippet of code, at every point in this snippet to keep track of all the values which are accessible. Okay? So the beginning is very simple. We just say we initialize some variable x to 0, then y to 1. Then when we call the function, we get access to a mutable borrow, so a pointer, which points to some value. And all what we care about is the value it points to. So here this value is x, that is 0. And we can compute it by using this purified version of choose, which is basically choose, but with 8 notions of pointers and borrows. And then we continue. So here is something interesting. I'm using the borrow z to do an in-place update. So this has a side effect. I'm updating x. But the important point is, because we're in Rust and we have this lifetime alpha here, which tells us that for as long as this borrow is alive, that is for as long as z is alive, we have to consider that those borrows are alive, which means that x and y are inaccessible. I can completely ignore x and y at this stage. All I need to say is, here, I have access to some pointer which points to a value which now is equal to 2. So this is what I do in the pure model. Okay? I defer the update to x. And finally, we get to the interesting part, which is we evaluate those assertions, and at this moment, in order to read x and y, we need to end the lifetime alpha. So we kill the borrow z, and we get access back to x and y, and at this moment, we can observe their values. So in the pure model, we say we get some new values for x and y. Now the question is, what are those new values? Well, because the Boolean is true, through choose we returned x, so through z we updated x, and y is left unchanged. So the new value for x is the last value we put in z, that is 2, and y is left unchanged. Now it is the case because the Boolean is true. If it was false, we would have the opposite. So we can actually write it this way. If true, then update x, otherwise we would have returned y, so update y. And now we see something which appears. At call site, we have to compute a purified version of the output from the inputs. And then later, when we end the lifetime alpha, we have to go the other way around. We have to propagate changes back into the environment, back into x and y. So we can write it this way. So at call site, we use this special choose function, which gives us a z, plus a function which consumes the last value of z at the moment we end the lifetime alpha, and gives us the updated values for x and y. And the way it does it is very simple. If b is true, it returns x, otherwise y, plus a function which consumes z and updates x and leaves y unchanged. Otherwise, we do the opposite. We return y plus a function which gives us an updated value for y. And this is the whole idea of the translation. This is a modular translation that is type-driven, and it's very important to make it work with what we call forward and backward functions. Okay? And it's very simple, but it works for a quite large subset of Rust with, for example, traits and loops, and it leads to, I think, is a quite idiomatic model. So let's see in practice how it works. So, okay. That's better. Okay, so I'm going to show you an example of the translation and a bit of proofs. So on the left, we have handwritten Rust code, and on the right, I've got the automatically generated lean model. So here we have the choose function, which is mostly like on the slides. Put aside the fact that we have this result type here. We have result type everywhere because functions can panic in Rust. We need to explicitly model that in the pure model. This multi-add-one function just performs an addition. So you can see we introduced an intermediate late binding there. This is a monadic late binding, so it's a bit like the question mark in Rust. X plus X can panic if there is an overflow, so we need to take that into account. So what this binding does is if x plus x overflows, we just evaluate to a failure result. Otherwise, we extract the value and we continue. Okay. This increment method is interesting because it takes a mutable borrow as input, but doesn't return any mutable borrow, contrary to choose. So in theory, so it returns a unit. So in theory, we should return a pair of a unit and a backward function for lifetime alpha. But the backward function doesn't consume anything. So here the backward function consumes the value we put in this borrow, but here there is none of them. So we actually directly return the updated value for x. So it's a bit of a state. When we don't return any mutable borrow, we get to some sort of a state passing style translation, right? And you can see here that we use it to increment x several times, and we just thread the value of x through the different function calls. We have support for recursion and loops. Loops get extracted to recursive functions. I'm going to skip that. I think you get the high-level idea. And finally, we have support for traits. So when we have a trait, like here, so for example, we have this counter trait, which is implemented if we provide an increment method, which increments self and returns a usize. In Lean, we model it with a structure, with one field per item in the trait. So here we say, very importantly, it works because our translation is modular. So in order to generate the model for the increment method, all we need to know is the signature of this increment method here. So we say that in the Lean model, we implement the trait counter if you implement a method which consumes an element of type self. So we make the type of self explicit here, while it's implicit on the left, and gives you a usize plus an updated value for self. Okay. Given that, we can easily generate the model for the instance of counter for usize, put everything together, and of course it works in the presence of polymorphic function. Like for example, this use counter function requires that T implements counter, and we model that by having this explicit input, which is counter of T, which we can use to call the increment method. Okay? So let's do some proofs. So, okay, we've got the model, and the point is to do, yes? Yeah, so we do it in several steps. So actually, the first step of the translation is to generate an incur function which actually returns a unit and a backward function which consumes nothing because there are no return borrows there, plus, so it directly returns the updated value, and then we collapse it. Because there is no point in returning a pair of a unit and a value. So we have a macropass which does this modification. Okay, so we've got this model. Let's see how we can do proofs. So I showed you this mul2add1 function, right? It's very simple, but we might want to prove that we're actually computing 2 times x plus 1, provided there is no overflow. So the way we can state and prove that is by writing a theorem which says that given some x, which is a machine integer, and the fact that x seen as an unbounded mathematical integer, so that's the meaning of this x.val notation, then if this is in bounds, then mul2add1 of x evaluates to some value, which is equal to what we expect. So then we do the proof in an interactive manner. And here we're really trying to make the proofs look like we're doing a debugging session. So here we want to basically dive into the body of the function, go through the function calls, and see if things fail. Okay? So when we do so, we work with an interactive state on the right, which shows us that we have x, which satisfies some preconditions. So the upper row, x is the same as x dot val, is just some syntactic sugar. And we have to prove this postcondition I showed. So the first step is to unfold the body, and then we can dive into it. Okay? So, for example, we want to kind of step through all the function calls. So here we have two of them, x plus x, then I plus 1. And we can do it by using this progress function. So if I go there, I see now it was able to go forward by one step. And now I've got a new context with I, which is a new integer, and which is equal to x plus x. Once again, I seen as a natural number is equal to x plus x seen as natural numbers. And then we can continue. Now we have I prime in the context, and we need to prove that I prime is equal to 2 times x plus 1, and we do so by using some arithmetic solver. And of course, the interesting thing is what happens if, say, I change the precondition, then when I get there, it will actually have to prove that there is no overflow, and it will not be able to do so. So it will tell me, okay, we have two things to prove. One is the same thing as before, but the other is that first you have to prove that there is no overflow. So x plus x is in bounds, and you can see, oh, I can't prove it. The precondition is not strong enough, so I should fix it, and then I can continue. Okay? So this is the overall approach. We state and prove theorems about the model, and then we go through it by using those tactics, which look a bit like we're doing a debugging session. Now, the big question is, of course, does it work in practice? Like, what about real applications? So I've shown you this on 2 lines of code function. What about a real cryptographic function? So there is an ongoing effort at Microsoft to port all the important cryptographic implementations of Symcrypt, which is the official cryptographic library of Windows, and to port all of those from trusted C code to verified Rust code. And we're starting with new implementations for post-quantum cryptography. There are many challenges, of course. The first one being that we have to verify low-level optimized code, as before. But also we want to verify and at the same time fix and improve the Rust code as written by the engineers. And this code has a very specific shape. So we have to adapt to what the engineers do, and we can't modify the code too much because, for example, of performance reasons. And also this code is evolving because we constantly need to optimize the code, for example, for specific architectures. So we have to be able to adapt to those modifications of the code, right? But verification is actually not the only challenge. There are other challenges. For example, the code must work for all environments currently targeted by Symcrypt, such as the Windows kernel, Xbox, or Azure Linux. And just to give you one example, when you compile the Windows kernel, you need to use features, for example, for hot patching, which are currently supported by MSVC but not LLVM. So these kind of problems are huge blockers to actually deploy Rust code in practice. And this is not linked to verification. It's also unclear that the Rust code is as fast as the C code, especially for this kind of low-level optimized code because of runtime branch checks, fat pointers, aliasing constraints, which force people to not write the code as they would if they had C. The size of the binary is important. We sometimes need to deploy the code in some firmware which is extremely constrained. And because of that, we can't have extremely modular implementations with a lot of traces everywhere, which get specialized and monomorphized because it leads to an explosion in the size of the binary. We need the code to be interoperable with C code. We need the code to be FIPS certified. So there are many constraints outside of verification, and which make verification even harder because the way we write the code is, well, very constrained. So the first target we're looking at is post-quantum cryptography. So first, an important question is, why do we want to deploy post-quantum cryptography today? And especially now as the biggest post-quantum computers don't have more than something like 100 qubits. And the reason is that even though post-quantum computers are not there yet, we're already vulnerable to a class of attacks which are called harvest now, decrypt later attacks. So if someone just saves the messages which are being exchanged on the internet, one day when the first computers are there, they can use them to break those messages. So we have to protect ourselves now. The first primitive we're targeting is MLChem, which is a key encapsulation mechanism, and it's the first primitive to be widely deployed, the first post-quantum primitive. The good thing with cryptography is that we have an extremely clear specification in the shape of the RFC. Once again, I'm focusing on functional correctness here. So for example, this is the RFC of the entity, number theoretic transform, which is one of the important parts of MLChem. Now, the Rust implementation doesn't look like that at all. For example, here we're using polynomials, which are arrays of finite numbers in a finite field. Oops, it moved a bit. On the right, we're using arrays of U16. Of course, we unfolded the loops. But most importantly, if you look here at those two lines of code, which compute a multiplication by some power of a constant zeta modulo some prime number 3329, in the implementation, it looks like this. So we have several arrays of pre-computed values. We have several small helpers. It's extremely low level, optimized, especially because it has to be constant time, etc. So the problem is that it is extremely unclear that our implementation actually implements the RFC, which is why we want to verify it. So we want to prove that the implementation does this, right? So the first step is to port the RFC to Lean, to formalize it in Lean. And the ported RFC looks like this. So we're putting in a lot of care to make sure that the RFC is as close as possible to the original NIST RFC. So as you can see, it's almost syntactically the same. Also, the specification, which is trusted, so if it's strong, then the verification effort is useless. The specification is executable and testable, which is important to make it more trustworthy. And something that is not obvious is that here, for example, here we have array accesses, and the bounds are statically checked. So when type checking the spec here, Lean checks that it can statically make sure that the bounds, that the indices are in bounds, and if it can't, then it rejects the spec. So all those are ways for us to make sure that the specification is trustworthy. Because once again, verification is made with regards to a trusted specification. And given this specification, we can prove the Lean theorem we want, which links the generated model to this spec entity. And what we say is that provided the input array is in bounds, so all the values, are smaller than 3329, then the output array seen as a polynomial is equal to calling the specification entity on the input array seen as a polynomial. So that's the methodology. So the original implementation was written in C, and it was rewritten to Rust by hand, leading to approximately 2,000 lines of code with, once again, tricky optimizations. Most of the work has been spent so far into improving the toolchain to have more models of the standard library, to have more automation. But the verification of the code itself is steadily moving forward, and we have verified 35% of the code so far. As I said, verification is not the only challenge. There are all those engineering and deployment issues. So for example, the problem of deployment to all the environments, such as the Windows kernel, Xbox, Azure, Linux, is solved by having this compiler URDC from Rust to C, and it's similar to what some other people do, for example, for boring SSL and OpenSSH. The performance is excellent. We have no performance penalty for the Rust code, which was not obvious, especially for the Syncrypt engineers who've been working with C for many years. For the size of the binary, we have a very controlled use of traits so that there is no explosion in the size. And we use other tricks to to have interoperable code, which can also be FIPS certified. I will not go into too many details here. So as a conclusion, we have this tool chain, which works by having this clean separation between the code and the proofs, and at its core works by having this compiler which generates a pure model from the original Rust code. We're currently working on Symcrypt and starting with MLChem. A midterm goal would be to have a complete verified TLS cipher suite, and on the longer term we want to extend this verification approach to a larger class of programs that is not only cryptographic code. Thanks for your attention.